Richard and I talked a couple weeks ago, and he mentioned he'd be covering quite a bit about soil. So the title in the program there is soil, but I'm going to talk more about soil and water and the management of soil water for these systems. I'm a professor in the Department of Renewable Resources at the University of Alberta, and my background is in soils and soil physics, which is basically the study of physical components in soils and the physical processes in soils, which includes the movement and transport of mass or water and solutes and energy in soils and heat. So really with managing soil water in these systems, and this talk is a little biased in terms of toward the irrigation, wastewater irrigation systems. We're really trying to manage the soil water balance. And so this little diagram here shows the components of the soil water balance. So basically the soil water balance treats the root zone as a bucket, if you want to be really bluntly simple about it. And we're basically trying to account for all the processes which bring water into that bucket and which allow water to leave that bucket. And in a soil plant system, we have water enters the soil through precipitation and irrigation, and in cold regions like ours through snowmelt as well. Water leaves the soil through evaporation from the soil surface, through transpiration through plants. So this is when plants take up the water and it moves through their tissues and then leaves through the leaves. And deep drainage or deep percolation, which is when there's more water in the soil root zone that the plant can take up, and so it drains below the root zone by gravity. So just to put that in words then, so we want to quantify the inputs into the root zone minus losses from the root zone, and the difference between the inputs and the losses is the change in the amount of water or the soil water storage in the root zone. And the diagram on the previous slide outlined all those different processes. And so for managing these systems, for managing water and irrigation scheduling and stuff, we want to understand this balance, and we want to try and measure as many components of it as possible, which will aid in our management decisions. So this is just very basic information, just talking about the different components of the root zone. This is probably all stuff you guys have taken in or heard of in previous experiences. So that's the soil water balance. Now there's some soil water properties that are very important when we're linking the soil water balance to a site-specific management scenario. Basically in terms of moisture content of the soil, we can have an oven dry soil, which basically means there's no moisture in the soil at all. And that means we actually take a soil sample and dry it out in an oven. And that's usually what you do in the lab before you do any kind of soil preparation or soil laboratory analysis or chemical analysis. The soil in a field will never get this dry. The other extreme is saturation, where essentially all the pores in the soil are full, and that's a fairly easy term to wrap your head around. Field capacity, you might hear people talk about this, is when the soil has less water than at saturation. The largest pores in the soil have drained under gravity, but now the moisture retention forces in the soil offset those gravitational forces. So you'll hear sometimes a couple days after a good rain, when all the water from the precipitation is infiltrated in the soil and then redistributed in the soil profile, that would be when the soil is at field capacity. And finally, wilting point, or permanent wilting point, it's called sometimes, is a water content which is less than field capacity but greater than oven dry. So basically this is the driest the soil will ever get in the field. And it's the water content of the soil at which the plant can no longer extract water out of the soil. So the soil is dry, there's very strong forces between the soil particles and the water that the plant can't overcome. And so transpiration effectively stops, and it may actually be a reverse situation. So the soil might actually suck water out of the plant, causing the plant to wilt. And plants have other mechanisms to, when the soil gets really dry, they close their stomata, their little pores in their leaves, to stop water loss. And this is a drought situation that hopefully we want to avoid. Okay. So these properties, these water properties, are unique for each soil. They're relatively easy to measure. And so now I guess I'll try and tie these properties into how they interact with the soil-water balance in terms of managing irrigation. So just to kind of show you here, a conceptual diagram, these are the strength of the attractive forces between soil particles and water from weak to strong. And on this axis here we have increasing size of water-filled pores. So these are different forces that occur in the soil. I won't get into the details of those, but we'll relate this to the terms that I just talked about here. This would be where you have strong forces. The strength or the forces between acting on the soil water are very strong. We have a dry soil. This would be at permanent wilting point here. Moist soil, where the water isn't held by the soil particles so strongly, and this is the plant available water range. And here we have a saturated soil here, where the water, the soil water, is prone to drainage or movement through the soil. Plants can still take up water at these very high water contents, but it's difficult because when the soil is saturated, we have low oxygen content in the soil, and plant roots need oxygen to survive. So prolonged periods of waterlogging in the soil aren't good for plants. They'll go into anaerobic respiration, and that will reduce their growth rate. So for irrigation management, we really want to keep the soil water content in this plant available water range, which is between field capacity and permanent wilting point. So the goals for water management in these Coppice systems, we want to, as John mentioned in the question period there, maximize transpiration by maintaining the soil water content between field capacity and permanent wilting point. And in semi-arid regions like Alberta, where we don't always have adequate and timely precipitation during the growing season, this is where we can use the irrigation to really manage and maximize this transpiration. By maximizing the transpiration, we'll also maximize the plant uptake of nutrients in the wastewater. So this is actually the main mechanism for wastewater treatment in these systems, is to take the nutrients that are in the wastewater that are potentially contaminants if released into other areas in the environment, and use them for growing fiber. And with the little caveat here that we still want to allow enough drainage to avoid salt accumulation in the root zone. And I'll talk a little bit about that. So basically, this is a soil physics conceptualization of the plant here. 3 sticks. So what we have here is we have water coming into the root zone either through precipitation or through irrigation. And these little plus signs here are salt crystals. This is dissolved salts in the water. That water enters the root zone, okay, through precipitation. The plant then extracts the water through transpiration, but the salts are left behind. So plants don't take up every salt that's out there. So these would be salts like calcium, sodium. Sodium's an especially bad one, as Richard talked about. Sulfate salts are very common in Alberta, or chloride salts are also sometimes common in other areas. So over time, if you don't have enough drainage below the root zone, you'll get more and more of these salts accumulating, and depending on the type of plant that you're growing, you may reach a threshold where the plant can't deal with the amount of salts in the root zone, and your plantation may fail. So the way, though, the good news is the way we can manage this is we can apply extra irrigation water to help flush these salts below the root zone. Right, so I just said that. We can apply excess irrigation water to encourage deep drainage or deep percolation below the root zone. This is usually done or easily done at the end of the growing season when the plants are no longer using water. So you just continue your irrigation after the plants are dormant for a little while. Or in our area here, this process may actually occur naturally during spring snowmelt when there's excess water and plants are still dormant. So that's assuming we have adequate snow in the winter. Isn't always the case. So one term you might hear when talking about the management of salts in the root zone is leaching fraction. And so this is, we're using our drainage and precipitation irrigation terms of our soil-water balance here. The leaching fraction is the ratio of drainage to precipitation plus irrigation. And so if you have a leaching fraction of 0, that means there's no drainage, and that over the long term, doesn't happen instantaneously, but over time, you may accumulate salts in the root zone. A leaching fraction of 1 is the other extreme, where you have just as much drainage as precipitation and irrigation, where you're moving lots of water through the root zone, and essentially that's inefficient use of wastewater. You're actually pumping water through the root zone faster than the plants can take it up in that case. So usually, depending on the site, a leaching fraction of 5 to 10% is adequate, but that's different for every location. So the way you would calculate this is you would need to understand the quality of your irrigation water, the chemistry, the salts dissolved in the irrigation water. You need to understand the soil properties, namely those permanent melting point and field capacity, the moisture retention properties of the soil, and be able to measure the other components of the soil-water balance. So I won't get into the specifics of that here, but I guess there's expertise out there that are available to help you make those decisions. So I'm I guess one of those sources of information, but there's other professionals out there that are able to help you with that as well. So in terms of recommendations, some of the basics that you need to manage soil water and the soil water balance at these Coppice sites is so we need to measure as many components of the soil water balance as possible on site and monitor them over time. And so precipitation and snow are easily measured with rain gauges or snow surveys. There's a whole network of meteorological stations that are managed by Alberta Agriculture that are available on our website. So even if you don't have equipment on site, you can find information from a place nearby. Environment Canada also has climate data online as well. You need to know how much irrigation you're applying, and this you can, your irrigation provider will have this available, probably using flow meters, so you know how much water is flowing through irrigation lines, etc. Soil water status. We need to know, to keep the soil water content between that field capacity and permanent wilting point range. We need to have timely and up-to-date measurements of soil water content or soil water energy or potential. And these are simple, inexpensive sensors now that can be installed. And with the technology these days, you can measure this every second if you want. Okay, it doesn't need to be that quick. You'll be drowned in data, but at least on a daily basis, you need to be able to track your soil moisture. Drainage. It's very difficult to measure drainage directly, but we can calculate it through other components if we know the other components of the soil water balance if we're measuring those. Transpiration is difficult to measure directly as well, but is calculated usually with other variables that are measured at the weather station on site. So air temperature, wind speed, solar radiation, and so the professionals you have there to assist you with these systems will be able to help you calculate these things. And soil monitoring. So, and this is probably in some of the provincial guidelines as well that Richard talked about. But if you want to be able to avoid or stay on top of the root zone salinization issue, for example, you need an annual assessment of root zone salinity and probably quite a few other chemical parameters. Okay, so and here, if you don't know yourself, find someone else that can help you. So hire or contract an irrigation manager who can interpret these measurements and translate them into an effective irrigation schedule.